Today is Friday, 20th of March, and this is now the third of our recorded lectures. So today, last time, let's walk over to the screen. Last time, I said we're going to start analyzing respiration, but I forgot we need to talk about water use efficiency and stomatal control. And in fact, today's lecture is necessary to answer part of question 8 on last year's take-home exam. What we're going to talk about today addresses that. And we're going to derive water use efficiency from what we call first principles, which is the principles of diffusion of gases. But before we get into that, a couple things. First of all, let me show you the homework. Everybody has this. This seems like old now, but it was the 14th of March. This was only 6 days ago. I sent you this key, but this is the key. This is an optional homework. And by the way, I've gotten most of the homeworks, nearly all, I think. They all came in this morning from the homework that's due today, which is comment on, tell me what you learned about the Kogan Homework. Lots of nice things people have sent. This is the optional homework that's mathematical, and it takes relative growth rate principles and predicts the future. And it says, if we do nothing, everyone in the United States will have the coronavirus in 47 days. But if we can go into lockdown and stay apart and wash our hands, we decrease the growth rate by a factor of 10, it will take 465 days or 1.3 years. That's what we're shooting for. So in a nutshell, this modeling, which you can do now in this class, is what all the premium epidemiologists all over the planet are working on, and trying to slow this down. So far, so good, but we'll take this day by day and see. Now, in the homework, I want to just review question 8. Just to review, this is a handout. You need to know energy transfer was 400 watts. This is question 6. It's 400 watts. I also didn't provide a value for sky radiation in here, and when there's no value, you either have to ask or assume a typical value. And to get the answer, I assumed 300 watts per meter squared coming from the sky. So question 6, assume the sky radiation is 300 watts per meter squared. That's a very typical value for sky radiation. Okay. And then of course, question 8, I think people know this, I sent it out. This said 110 here, it says 100 here. This number should be 110, so they match. And when they are, we get this. This is a hard question. This was a hard exam, but it's a take-home exam. So now we're going to take a look at water use efficiency. And I might start this by telling you that if you were maybe 15 years older, you would have taken plant physiology using this textbook right here. And this is the best-selling textbook in the world, and it's written by, let's see if I can do this. First of all, it's dedicated to Herman Weedy, who taught plant physiology on this campus for about 35 years in a row. And I don't think maybe their pictures aren't in this book. But this is written by Frank Salisbury, who taught plant physiology here for many years, and he spent all this time working on this textbook. But it was a great textbook, and it has guest essays from people that did stuff. So I gave this lecture that I'm about to give I did a guest lecture in his class, and he liked it so much that when he did the next edition of his book, he put this lecture as a guest essay, how to calculate water use efficiency from first principles. So for a little while I was famous because I made this plant physiology textbook. And then he put a picture of me, and it's a good thing you can't see this because I was like 35 years younger then when I did this. So, let's take first water use efficiency. This is from last time. We cleaned the board for a new lecture, but I didn't erase this. 1 gram per 600 grams of water, 1 gram per 300 grams of water, C4, 1 to 80. We can derive these values from the rates of diffusion of gases. And this is just staggering. And in fact, let's take a look at these. How typical are these values? Here is from the textbook. Get this off of here. I don't want to zoom in because you want to be able to see this whole thing. It's pretty hard to see this, but there, I can zoom in a little. 2 C4 crops, maize and sorghum. I'll send this as a handout. And then a whole bunch of C3 crops. Wyatt's favorite crop, potatoes and wheat, soybeans, alfalfa. How much water did they use? What was the yield they produced? And the ratio of yield to water is the water use efficiency. Now, you can express it 2 ways. Water use efficiency, that's getting a little bit tired. Let's try a different color. Water use efficiency, which is how we usually describe it, is yield over water. And can you see this back there? This is a light marker. I'm going to go to a darker marker. 1 over this, water use requirement, WUR, is just the inverse. That's water over yield. And we can call this efficiency because we can do yield in grams and we can do water in grams. Same thing down here, grams and grams. So let's take C3. We're saying 1 gram of, this is dry weight, per 600 grams of water. Let me show you how staggering that is. So this morning, we did some analysis. 1 paper clip weighs a gram. If we put this on the balance, we could walk over here and measure it. Now it turns out a big paper clip is a little more than a gram, and a little paper clip's a little under, but still, and then there's coated paper clips, but they, one gram for a paper clip. Now, let me walk over here. Yeah, this is on the big side here. This is a 500 ml beaker. If we fill this right to the top, it'd be about 600 mils of water. It takes this much water to make this much yield. Oh man, it's a terrible ratio. We're out of water, and this is all we can get from that. Let's analyze what we can do about it. And this is such a profound question. When 5 years ago, when I got asked to do a TED Talk, I talked exactly about this. Only it's a 15-minute talk, so all the details are gone in that talk, just the concepts. But this is pretty bad. Let's take a look at this. If we go way over here, this is grams per kilogram of water. C4 in this were about C4 in this were about, can you see this, 2.5 per 1,000, and so that comes out to be about 1 gram per 400 grams of water. So this table is even slightly worse than the number I wrote up here. The C3 crops in this come out to be about 1.5 per 1,000 grams. And that comes out to be about, that's pretty close, 1 gram per 600 for C3. C4 is slightly better, of course, CAM are really good. Paul Kasuma this morning looked up some more values, and you can find this stuff all over on the internet. Here's average, this is crops in India, average for wheat, rice, and wheat, and this is, the units are kilograms per cubic meter, but a 1 is 1 to 1,000 here. And so these numbers don't even get to 1. So by some estimates, the water use efficiency is even worse than this chart. It depends on the crop some. It also depends on how much water is wasted and when the crop is growing. Is it in a hot season? As an example, cotton uses, it's terrible water use efficiency. Well, it needs to be grown when it's hot and the vapor pressure deficit is huge, so it goes through a lot of water. Rice typically uses a lot of water because water evaporates from the surface. It's growing flooded and water's evaporating. So here's a definition of water use efficiency. W-U-E. If we go over and ask our irrigation engineers, how do you define this? That's an E. T over ET. What's that mean?
Temperature.
In this case, T means transpiration. Transpiration, T-R-A-N-S-P. And if that's transpiration, what's ET? Evapotranspiration. So, what's the difference? Look, if we have a crop like this, let's see, here's our crop. Green, here's the ground, roots. Now we're going to have a blue marker. If water comes out of the leaf, that's transpiration. If water comes out of the ground, that's evaporation. So when it's the same principles, the same latent heat of evaporation, but if it's coming out of a leaf, it's called transpiration. Ground is E. If you have a bad crop, or a small crop and a lot of water, E can be enormous. So the whole goal of irrigation engineering is to get T really big and E really small. And sometimes they get 60%, and then we start to do subsurface drip irrigation, where we put the water down here so the evaporation is tiny. This is all terrific, and it's saved a lot of water. But to a plant physiologist, this is irrigation engineer, WUE, is transpiration, oops, it's efficiency. It's yield over transpiration. This water that went through the plant, how efficiently was it used? How good can we get this ratio? To an irrigation engineer, they say, oh no, we got the water in the plant. That was our job. We're done. It all went through the plant. these numbers right here relate to these numbers over here. So how would we calculate this? As a general rule, if we make a graph right here of T, transpiration, now this could be per day or per season, and we do yield over here. It's a straight line. It's a very accurate way to predict yield if you know how much water went through the plant. Not ET, just the T. But what can we do about this? Is the whole line straight? As physiologists, how could we use this water more efficiently? So what we're going to take now is, I'll put this in green, and hopefully you can see that. Good enough, I think. One stomate. We're going to analyze all the water on the planet based on one stomate. As you know, now we're going to do blue. As you know, the water comes out by diffusion, comes out of the leaf, and you've already calculated the vapor pressure deficit, VPD, and that is the humidity inside the leaf with units of kilopascals, and the humidity ambient, A, is for ambient outside the leaf, which is also in kilopascals. And this is absolute humidity. So this goes back to calculations you did several weeks ago. And this difference, VPD, is really HI minus HA. That's how much water comes out of the leaf. Now, shown in black because carbon is in black. On through the exact same stomate, CO2 goes in. And it's two gases going through the same tiny little hole multiplied by billions and billions of stomates. And over here, we call this CI, inside. CO2 inside, water vapor inside. Now, remember that once we get CO2, it goes right to CO2. So what we can do from this simple example is analyze the ratio of CO2 coming in to water going out. And that is water use efficiency. And the beauty of this is based on diffusion of gases. So if we count right, let me put this right here. We're going to do a little bit more applied. P net over transpiration. P net leads to yield. So this ratio is water use efficiency. Now, when we write transpiration, we can say that delta H, delta H2O, times conductance to water equals transpiration. You can write it like this. And then we did this is H2O. We did this before. If you know the gradient, and we know this, we know Stomatal conductance, this exact same equation, what did I write it in black, applies to photosynthesis. Delta CO2 for that times conductance to CO2 equals photosynthesis. So you can see how we're building on this, and all of a sudden we made this jump from gases and stomates to calculate water use efficiency. So what we need to do is two things. Let me take one more step here. I need to give myself plenty of room. We'll erase this transpiration. To be more detailed, this is CA minus CI times conductance over HI minus HA times conductance to water. So we need to know conductance and we need to know driving gradients. We can measure CA, that's just ambient CO2, easy to measure. We can measure absolute humidity of the air, easy to measure. We can get HI because we assume this is 100% humidity. So as soon as we know temp of the leaf times 100% RH is HI. So we can get HI. To solve this, we got to figure out CI and these conductances. So here's how we do this. First, we take this conductance. We clamp on the leaf with a gas exchange system. You could look up a typical value of conductance, but we measure this by measuring transpiration. There's various ways to measure that. And calculating these two, and guess what? I'm going to rearrange this and write this over here. GH2O equals transpiration over HI minus HA. So we've measured all of these, we calculate conductance to water vapor. And this is exactly how all of these instruments work. Here is a picture. We own a Clampon Leader to do this. They're not cheap, but this meter calculates everything in here and gives you a nice digital readout. And here's a graduate student with a portable one. There's several companies that make these, and Shu Young. We don't have it. Oh yeah, look at this.
That's it.
Look at that.
They've been using it for one of my other classes.
Cool. There we go. Just like the picture. I forgot this is in here. We have another one and we're using that. Here we go. This is the instrument we're talking about. You clamp on a leaf. It measures all these things in solid form. Now, only about 5% of the people that use these know how they work. It's just a digital number. But if you understand how they work, you can tell when you're getting bad data. And that's pretty important, even though it solves all the equations. I got some other pictures of that. Here's a picture of the readout, and now the modern ones not only get all these buttons, but they give you a graph. Here's another student measuring in the field. These are all to calculate water use efficiency of a leaf, and they do photosynthesis and everything else as well. All right. So we've done this, we get a value for GH2O. And I'll give you a handout with everything worked out and just show the principles. Now, this is an amazing step. Over here, these two gases are working by diffusion, and if one's going in through that hole, one's coming out through that hole, we can calculate how fast the other one's going in. Because they're the ideal gas law, all gases are created equal. So if we know the conductance to water coming out, we know the conductance of CO2 going in. Cool. So all of a sudden, boom, we can go from here to here, and now we only have one variable left, CI. We can solve this whole thing for water use efficiency, but there's one key step, and I can emphasize this, we've drawn it right here. If we do, I'm gonna have black. If we do, C is 12, oxygen is 16. There's CO2, a scale drawing of CO2. Oxygen's bigger than the C. Now let's do H2O. H is 1. It's teeny. Guess what? The speed at which gases move is inversely proportional to their size. So water vapor, the diffusion rate of water vapor, is way faster than the diffusion rate of CO2. So if these stomates open just a little bit, the water comes pouring out, and this big CO2 molecule is having trouble getting in. These are like little third graders diffusing around fast, and this is some 80-year-old. And if this room was the inside of a stomate, then the door was the stomata. The third graders would be diffusing by random out the door pretty fast, and the old timers would have trouble getting in because they're moving slow. So the speed is inversely proportional to the mass, but it's the square root of the mass. The speed of diffusion is inversely proportional to the mass. Now, this one, we know this is 44, 16, 12, 16, and we know this is 16, 1 plus 16 plus 1, we know this is 18. So CO2, the water, is moving faster than CO2, and we can write this as the ratio of CO2 to the ratio of H2O equals the square root of 18 over the square root of 44. I think I have this right there. Check my math. Does that look right, Shu Young?
Mm-hmm.
And because this is the same thing as the square root of 18 over the square root of 44, mathematically it's just a shortcut. And this comes out to be 0.625. So CO2 moves 62% as fast as water vapor, directly because of the size of the molecules. This is worked out in a handout I'm going to give you. But it's all we want to know right now is the ratio of these. So over here, we can measure conductance to water vapor with our instruments. This one we can't get, we have to calculate it. And guess what? It's equal to 0.625 times conductance to water. I should write this as a subscript here. 625 conductance to H2O. So now, the H2Os cancel. The actual conductance doesn't matter because it cancels. And now this whole equation is delta CO2 over delta H2O times 0.625. And that is water use efficiency from first the principles. I've got some handouts that show worked out examples of this. But let's work through one, because do we have these kind of numbers when we do this? And let's see.
Excuse me,
Yes?
in this equation, like CO2 moves 62.5 times greater than H2O.
This would be 62.5%.
Faster than H2O.
Slower,
Slower.
because it's bigger.
Yeah.
So that's why I draw it like this, because it moves slower because it's a bigger molecule. You always got to remember the molecular weights to make sure you've got the 0.625 times the right thing. Usually we don't call it 62.5%, but it is same thing. So let's work on an example. I mean, if this is diffusion of gases, wow, you know, why doesn't more CO2 get into the plant? Here's the fundamental problem. I'm going to put this way over here. No, right here. Right here. These two numbers. Sammy, I'm going to erase this so we can get some room to write. How much water vapor is in the air? This goes back to, you've calculated this before, but this psychometric curve, let me see. I'm going to zoom out so we get the whole thing. But at about 25 degrees C, there is about 3 kilopascals of water vapor in the air. And if it's, let me see if I should work an example that's the same as my handout, maybe.
And what temperature is that at?
This is at about 25. But this is divided by barometric pressure. Let's just leave this. There's about 3 kilopascals in the air. How much, now this one, years and years ago, people never knew this, now everybody knows it. How much CO2 is in the air? It's going up, but about how much is, what's in a round number, what's the CO2 in our atmosphere?
What, 410 or 415 something?
450, we're not there yet.
415,
But
sorry.
a couple, 415. A couple of years ago, we passed 400. 400 what? What are the units? Parts per million. So 400 ppm is exactly equal to 400 micromoles of CO2 per mole of air. That parts per million is just a very shortcut way to write micromoles per mole, because it's a mixing ratio of it. And this is where we get into my famous beads, which I conveniently have right here. Nitrogen, inert filler gas in the air. Oxygen, plenty of oxygen in the air. Water vapor. 3, but it's 3 what? To match water vapor to this, 3 kilopascals to, let's do this for sea level, roughly 100 kilopascals. This is air pressure, and this is H2O pressure, kPa H2O. Here's another amazing conversion, and this is why we measure water vapor and pressure because this is numerically equal to moles per mole. Pressure of a gas divided by total air pressure is equal to mole fraction. Because of the ideal gas law, they're all equal. So suddenly, guess what? We got our driving gradients in the same units. This one is micromoles per mole. This one, and this would come out to be in our example here, 0.03 moles of water vapor. I could put that one in blue, couldn't I? For moles of H2O. And this one is moles of air. This is another beauty of working from first principles. So now,
That's 1 mole of air, right?
this is 1 mole.
And then on the water vapor side.
And this is 1 mole here too. That's correct. Both of them are for 1 mole. So, look at the driving gradients for CO2 in the air. This one, let's put them, this would be equal to 0.4 millimoles per mole. And this one is 0.3 moles is 30 millimoles per mole of air. Multiplying by 1,000 in the exact same units. Now, you tell me why it takes so much water to grow food. This number is almost 100 times bigger than this number. There's the fundamental problem. Water vapor is pouring out because there's almost 100 times as much water vapor in the air. It's not quite 100. This would be the case if it was 0% humidity. That's not. There's some humidity in the air, but you still get the point. This is CO2, and this is H2O on the exact same basis. So to emphasize this whole thing is 1,000 little beads, so to scale, there's 4 in here, 4 CO2s, and here's this plant trying to get 4 CO2s and the water is just pouring out. And that's why it's such a big problem. For people, we would use a lot of water too, but look at for us. The oxygen coming in, there's plenty of it. We don't have to lose very much water. We don't have to lose very much water because there's so much oxygen in the air. There's something like 600 times more oxygen in the air than there is CO2. So plants have it 600 times harder than people to get CO2 without losing water. Sam?
So then if CO2 increases, water use efficiency increases?
Yes, it does. If CO2 increases, water use efficiency increases. And now look at this. If you were in graduate school with me, this was about 0.3. That's a big increase. This was more like when I was in high school, but still, that's a big increase. That's 33% increase.
So global warming is good for that.
So global, well, not global warming,
Global CO2.
global elevated CO2 fundamentally makes plants more water use efficient. And that's a big deal. And people have said, what are you worried about? Plants are going to get more water use efficient. Isn't that good? Yes, it is. But if global warming is associated with erratic rainfall, we can't grow plants without water. They can be more efficient, but they still got to have water. But this is fundamental. It does help, and in fact, we have seen that. You look at these tables that I showed up here. This is the one I just put up here. If this is 30, 40 years old, we can do better than this now, because of a little bit better, because of higher CO2. Same thing with if we put more oxygen in the air, we could all run faster because we have be easier to breathe. Same concept. Now for us, we're ventilating. Plants can't do that. It all has to happen by diffusion. They're not pumping anything, it's just diffusion. That's why my old people and third graders analogy is pretty good, because you can remember that. So, we still didn't get, let's put some numbers down here. Let's go right to here. Let's put, if we do this in millimoles, we're going to put 0.4 millimoles, and HA down here, we're going to put 30 millimoles. I can erase some of this so you can see it. There's two of our numbers. This cancels. How about HI? Let's say, HI should be 30 millimoles, because that's 25 degrees, about 25 degrees, 100% RH is about 3 kilopascals. Now let's take a humidity of 10%, which it gets to 10% around in Utah in a day. So HA is, if the air temperature is the same, HA is 3 times 10% humidity, 0.3. You see what I just did? It's calculate HI, and if it's 10% humidity, that's 0.3. Oops. 3, yeah, it's in millimoles, this is 3 millimoles, 10% of this number. So now the delta H equals 30 minus 3, 27 millimoles. How about the delta CO2? It's 0.4. Now, typically, we assume that CI equals about 2/3 of CA. This is a rule of thumb for C3 plants. We can calculate this with this instrument, but a rule of thumb, so if this is 400, what's 2/3 of 400? We could calculate it exactly. 0.67 would be about
266.66.
how about 267 ppm for internal. Now, that's when we put that in millimoles, 0.4, 0.267, and what's this difference? 0.133 for the delta CO2, it's over here. CO2. Gotta leave room for here we go. 0.4 minus 0.267 equals 0.133, and that's the units of this are millimoles per mole of air. So to take this down here, 0.133, we're almost here, over 27, but we gotta take this times 0.625. Now, we'll then do 1.133 times 0.625, it's gonna be about 1.
Zero point one three three times 0.625.
Yeah,
I got,
0.1.
I actually got close to 0.1. 0.08.
Okay, even a little bit lower, 0.08. And this one is still 27. Now what's the water use? 0.08 divided by 27.
0.003.
That's the water use efficiency.
Dang.
3 grams per liter. So 3 paper clips per liter of water. Where's my liter? Here. Here's a liter. That's our water use efficiency calculated from first principles. Pretty low. And we say, what can we do about this? Man, this is terrible. I mean, we gotta do something about this. You can see all the politicians running around at this point. We gotta do something about this. Well, what can we do? Let's close the stomates. That's like telling people, just quit breathing. You're using too much water. Nah. You close the stomates and they're not gonna get CO2. So that doesn't help.
Zero.
Because they gotta go through the same opening here. There's no options. And cool the leaf. That would help. If the leaf gets cooler, but then how does the leaf cool now? Well, by evaporating water. So that's how it stays cool. And so you could say we could shade the leaf. Well, sure, and sometimes there's evidence now we can shade things. And one of the big things now is agrivoltaics. You guys ever heard of that? Stands for agricultural solar photovoltaics. You can look it up, agrivoltaics, on the internet. Because people are so water limited, I'm gonna draw a picture of this. It's a big deal. Here is our crop field. I'm gonna need a new green marker. This one's getting. Here's our crop field. Where's my yellow? Here's the sun beating down on this and making water go up like that. And a lot of water. Now we say, oh, the plants are hot, they're out there in the full sun. We're gonna put solar panels up here over the crop. Solar PV, photovoltaics. We'll shade the crop and we'll make electricity. What's wrong with that?
Photosynthesis.
Yeah, photosynthesis needs light. So, and this is partial shading. So it's okay, we don't want to block it, we'll make these smaller. But in places that are out of water, we're starting to do this. Because water is limiting, the yield might get cut to 2/3, but the water might get cut in half because the crop is cooler. And remember our light response curve? If PPFD, photosynthetic photon flux density, and PNet. If we're up here, not too good, you cut the light in half, and we're down here. So we did reduce yield, but we didn't cut it as much as water. And really, if we make this curve for water with light, the water kind of is linear, just goes up. So there's some value of trying to cool the crops by putting solar panels on. And it's all economics. What's the electricity worth? You gotta put them high enough so you can drive your tractor under them, and it's a lot of complications. But there's billions of dollars of venture capital going into this right now to try and use less water in food production and get some electricity out of it. You can see the problem when they're just fundamentally going through the same thing. You could say, well, we're working on it, we're raising this. You know, that makes it a little better. Here's the point I want to make. Back to this. Ta-da! T-shirt with the red C4 on the chest. We bring in C4, look what happens. Over here, C4 has their double pump to suck CO2. C3 on average is 2/3. C4 on average is 1/3. It's twice as good as C3 at sucking CO2 down. And guess what? If it's twice as good, this delta CO2 gets twice as big, and the water use efficiency is doubled because of that. And in fact, that's why we got 1 to 600 and 1 to 300 over here for C4. These are rules of thumb. So again, what did we get here? 0.003. Isn't that about 1 to 300? I think it is. It's 3 over 1,000. It's about 1 to 300. So we derive this from our humidity over there. We assume 10% humidity in this example, which is pretty low. Now look at camp plants. They got
What about if we limit evapotranspiration?
Well, if our colleagues in irrigation engineering come in and they make the E part really little, like if they do E, T, then that helps a lot, for sure. But this usually happens from, and that's a good point because this is good. Drip irrigation reduces evaporation. That's why we try and do drip irrigation. Plus it can be more precision. Sprinklers are the worst. Overhead irrigating, they're easy, but water's evaporating in the air. You know, that's the E is big with sprinkler irrigation.
Night irrigation? Night irrigation?
Night, yeah, absolutely. Night irrigation is better than day because the pressure deficit is smaller and more water gets to the ground. So this is big, but this is irrigation engineering. Our part of it is trying to make this part better. So they both matter. We could say, look, what if we combine these? We could say, well, we want yield over ET. W-U-E. That would combine both of these into one equation. So, let me see if I'm going to send you these handouts because let me show them to you here and then you know what's coming. Calculating water use efficiency from first principles. Photosynthesis over transpiration, driving gradients. This just works through what I just did on the board. And then down here, it gets you to water use efficiency in moles per mole. Now we did 0.003 right here. That didn't help. There. And with these, I got 0.0025. So it's the worked out example is pretty close to what we chose. But look at the units. This is moles per mole. These are grams per gram. This is a key distinction now So now, we turn this over. Let me put this on the board. We can't directly compare these yet because I'm out of room, but I can put it all the way over here. We have a mole of CH2O. Can you see this okay in that thing? Per mole of H2O. And yield, guess what? That's 30 grams per mole. And this is 18 grams per mole. So when we do weight per weight, this is 30. Water use efficiency gets a little better, almost twice as good on a weight per weight basis. Because this is going to be grams, and that's going to be grams. So we got to do that conversion. We had to get to mole per mole to get diffusion of gases to fundamental, but then after we got that, we can go back to weight of this. And the second side of this shows exactly that. And in this example, we're at 4, but in the next lecture, we'll talk about respiration. All of this stuff on the board and this over here is grams of sucrose per gram of water. And even sugar cane is not pure sucrose. Now we bring in respiration. And some of this sucrose gets metabolized to make proteins, it gets metabolized to make Rubisco, to lipids, cellulose. That's respiration. And that's the next step to get the biomass. And I've shown that in this handout that's coming. I've shown it in here. So one of the things, Sammy, you didn't suggest, why don't we just grow our crops where the humidity is very high? And that's one of the potential solutions. But a lot of places where we have low humidity means we have really good sunlight. So high humidity means clouds, and then you have less photosynthesis. Depends on what we're out of. If we're out of sunlight, or we're out of water. But that's this relative humidity right here. It definitely helps to have high humidity. Okay. This is everything I want to talk about today. Deriving water use efficiency from first principles. The exam is next class period. It's next Wednesday, and I will email the exam on Wednesday. You have 24 hours to work the exam, so block out that time to work the exam. Monday evening, we're going to try and do a review. I'll try to go through the old tests to work out the old tests, so try and do that in advance. Normally our review is Tuesday, but to give you more time to think about it, I'm going to do it on Monday. That's just a recorded video. No homework, you can work the exam, plenty of stuff in there, and related questions. But now with this lecture, you can work question 8 too in the test. That's it. I will see you Wednesday. I plan to record another lecture, even though I give you the exam. But nothing in that lecture will be on the take-home. Everything is up to the day. See you next Wednesday.